And so it's very nice to be back. And in my talk, I want to give you a little bit of an overview of the research that we're doing, which is really trying to apply quantum theory to the early universe. And so the talk will be less technical than the standard physics talk. I hope it's not too technical, so really if there are things that are really unclear, please do interrupt me, because it's also a bit pointless if I just keep going and you don't know what I'm talking about. Well, let me start with things that probably you are much more aware of than I am, but which is the history of cosmology. If we go back just a little over 100 years, in fact, surprisingly little was known about the universe on large scales. It wasn't clear, in fact, that whether we had one galaxy or many. There were, astronomers observed the stars and they observed a number of clouds, and it wasn't clear what these clouds were. The prevalent hypothesis was that these were sort of solar systems in formation, which turned out to be partly true. Right? So some of these clouds really are dust clouds which are collapsing and which will form stars and eventually planets around them. But this was not necessarily true of all of them. Then in the 1910s, a number of people started making, with improved telescopes and spectrometers, people started making measurements of the speeds of some of these objects. And they, in particular, Vastus Leifer was the first one to make sort of significant and precise measurements. And he published a report on this in 1917, where he was saying, that many of the stars which we see have typical velocities of about, say, 20 kilometers per second. It can be 10, it can be 40, it depends, right? But on the order of 20 kilometers a second, with respect to us. And in all sorts of directions, in random directions. But then he was measuring some of these clouds to have speeds on the order of 500 kilometers per second. Now, then he was saying, well, if this grouping of objects is supposed to have coexisted for a long time, that doesn't make any sense. Because some of these objects are moving so fast, there is, the chance that they just happen to be in one place right now is really minuscule. Right? So we should see these objects so some of these objects must be much further away than we think. They cannot all be the same object. So this was the first real evidence that there cannot be one large structure in the universe, but then that in fact there are many galaxies in the universe. This was in 1917, just 2 years, or maybe a little over a year after Einstein formulated his theory of relativity. So this Leifer, who was an observational astronomer, was not aware of this theory at all. So he had no concept that this could mean that there are other objects that that the universe is expanding or anything like this. He could only, this was not something that was conceptually possible for him. He just noticed this and concluded that this cannot be, there cannot be just one galaxy. And then in the 1920s, these measurements were continued, and the most famous person to do this was Hubble, and in the end Hubble got all the credit for this, even though actually Leifer should probably get the credit. And then together with a number of theorists like Friedman, Lemaitre, and also de Sitter and Einstein himself, the picture emerged that the universe itself is expanding. Because it was then also noticed that not only are the typical speeds of some of these clouds, which were then found to be galaxies, are they very large, they are also larger the further away these objects are, and moreover, almost all of them are moving away from each other. Right. There's only a few which are very close by, which due to gravitational attraction are moving towards us, but on the whole, everything is moving apart. And so this picture of the expanding universe emerged just, almost 100 years ago. But of course, this is now a major conceptual change. Right? The fact that the universe is expanding means that the universe is changing over time. It was always thought before, or it was implicitly assumed, that time and space are just sort of an unchanging arena in which physics takes place. But now, if the universe is evolving, of course, it completely changes the concept of space and time, because now space and time are seen to actually to evolve, to have a history themselves. In fact, also just to clarify, it's just the space between galaxies which is expanding. The galaxies themselves, because of the gravitational interaction, the metric is different in the region where you have the galaxies, and so the galaxies remain of roughly constant size, but the distance between them is evolving. So from this first conceptual leap, there came immediately the second one, which is if we now go back in time, well then everything was closer together. And if we go back far enough, then we reach the moment where everything was right on top of each other. And this is what we now call the Big Bang. Maybe more precisely, one should say that what you get when you go back in time is that the universe got denser and denser and hotter. And so we get to this idea that there must have been an extremely dense, extremely hot initial phase. Right? Whether this was some kind of explosion or not is something that one should bear in mind, that this is not very clear yet. And I will give some arguments in a minute for why this viewpoint is probably wrong. Now, do we have any evidence for this? Right? I mean, you can ask, of course, and you should ask in science, is this just speculation? Do we have evidence for this? And there is quite good evidence for this hot, dense initial phase. The best evidence we have is the cosmic background radiation. This can be thought of as the radiation that's left over from the early universe. So very early on, when the universe was very hot and dense, the average energy was so high that no atoms could form. I mean, the electrons had so much energy that they were not bound to the nucleus, and they would just fly around freely. But if you have free electrons flying around, and you have light, photons, also flying around, they interact very strongly because of electromagnetic interactions. And so the light doesn't fly, photons cannot fly very far in a straight line before they bounce off some electron. And this had the consequence that the early universe was not transparent. Right? Because we can see each other very well, because light can fly in a straight line between us. Therefore we can see each other clearly. But if light in between was constantly bouncing off some free electrons, we would not see each other. And this is exactly how it was in the early universe. And then when the universe cooled enough for the first atoms to form, all this light could suddenly fly freely and was, in a sense, released into the universe. And this happened everywhere. And this light was then also flying in all directions. And this radiation is still left over in the universe. It's now much... when it was released, the universe was 1,000 times smaller than it is now. And it was also 1,000 times hotter. So the temperature at that time was 3,000 degrees Kelvin, and this radiation, because the universe expanded by a factor of 1,000, cooled down to just 3 degrees Kelvin now. So this also means that the wavelength of this radiation got 1,000 times longer because of the expansion of the universe, and it's now in the microwave bandwidth mostly. And that's why it's sometimes also called the cosmic microwave background radiation. And this can be measured. Here's a picture taken by the Planck satellite, which shows the radiation in false colors because it's microwave radiation, in all directions in the sky. It just shows that there are small differences in temperature in different directions. And these early changes in temperature were also early changes in density, and in the later universe, this led to some regions forming galaxies and some regions forming voids where there is nothing. So that's good evidence for the Big Bang. Another very good evidence is the abundances of elements in the early universe. So if you can calculate from the expansion history of the universe how much hydrogen, helium, lithium there should be in the universe, and the measured quantities of in old stars systems match these predictions extremely well. So this is again strong evidence that there was this early hot dense phase. Another piece of evidence which is not so often emphasized is the fact that the sky is dark at night. If the universe was eternal, and if there were stars everywhere, in all directions, then wherever you would look, there would be light from a star arriving here. And then it would never be dark. It's just that, the universe, there were not when we look back in time, we don't see stars all the way. There is a point where we look back far enough that there were no stars. And this is then why the sky is actually dark. Now, there was some discussion in the early days of relativity whether the Big Bang was really, whether it could just be an artifact of the equations. So there was not much debate, I guess, after some point, at least certainly after the discovery of the microwave background, there was no debate anymore whether there was a hot, dense initial phase. But there was a debate whether really when the universe contracts, whether it really goes into a singularity or not. People thought, a number of people thought, including Einstein in the early days, that this was an artifact of assuming too much symmetry in solving the equations. That in fact, due to the anisotropies in the universe, some directions would shrink faster and others would not shrink so fast, some directions in space, and so that actually, in a sense, you would not everything would shrink to a point, but some directions would shrink faster, but then re-expand again, and then others would shrink more slowly, and that the whole thing would be an anisotropic Big Bang, but that it would just go through because of these anisotropies, that having this singularity, that this was just because you assume that everything is contracting at exactly the same rate in all directions. And this was thought to be unrealistic. Well, it is unrealistic. But the question is whether the outcome is also unrealistic or not. And after people studied this some more, they found that in fact, yes, it's certainly true that the universe, when it contracts, it becomes more and more anisotropic, meaning it will contract differently in different regions, and in some places faster, in others less fast, but still everywhere you reach zero size eventually. So you take a certain region of the universe, you go back, and it will go into a singularity. It will reach, sort of, classically speaking, it will reach infinite curvature. And this was made most clearly by the singularity theorems that Roger Penrose and Stephen Hawking could then prove in the 60s and 70s. And where they showed that under rather general conditions on what kind of matter is in the universe and what sort of average geometry the universe has. And under fairly general conditions, you can show by a theorem that in fact a singularity is unavoidable in the past. There are ways of avoiding these conditions for the theorems. So it is not absolutely watertight, but these require either exotic types of matter, which we don't know if they exist or not, or they require special conditions, and the fact that the universe would have to be spatially closed in the early universe, which is a possibility.
The question about the previous diagram.
Yes.
It makes it look like there would be many different points in the Big Bang.
Yes.
Is that a possibility, or?
Yes. I will explain that actually. Momentarily, I will explain it in a bit more detail. But that is in fact the typical picture, which is not how it's usually presented. But I'll come to that. And sorry, here I was here. So the singularity theorems imply that typically this is what happens, that you get a singularity. And then this led to the idea that maybe this was also the beginning of the universe. But one should bear in mind that that's actually really just sort of a bit of I don't know. This is the point where you can't continue, and then you just say, oh, okay, so something special must have happened. And then people said that something very special must have happened, space and time could have begun there. But really, all the singularity theorems are saying is that our theory of general relativity breaks down at this point. And the fact that it breaks down doesn't mean that it must be the beginning of the universe, but that was sort of the assumption that people then made. The reason why this is a slightly strange assumption to make is the following. So the picture that people typically have in mind is this one. We have the universe, we go back in time, the universe shrinks, here is the region where it's transparent, here is the emission of the microwave background, we get to the hot dense phase, everything goes together in one point. That's the Big Bang. Now that's the picture which normally people had in mind, and I think it also, the idea spread very rapidly because it has a number of religious connotations and has this creation myth built in, which, as you are, of course, well aware, is something that people have had in their minds for a long time, in various forms, in different cultures. And this is, however, not really what the geometry did. So if you know... now, one should say that we don't really know how large the universe is, because we cannot see arbitrarily far. But what you can do is you can already take the part of the universe which we do know to exist. So take the observable part of the universe and just evolve it back in time using Einstein's equations. Then, as we go back in time, the universe did indeed get smaller, but it didn't, in a sense, it became younger faster than it became smaller. So, if you imagine that everything goes to a point, you would expect that this would happen in proportion, that really the universe would become small at the same rate, in a sense, as it became young. But this is not what the equations tell you. So, for instance, as an example, if you go back to a microsecond after where you think the Big Bang should be, just go to... This microsecond is completely arbitrary. I'm just taking this as an example. You can do this for any amount of time that you like. But let's say a microsecond for definiteness. Then, during this time, light can fly 300 meters. So you would expect that the size of the universe would have to be on the order of, also 1 microsecond in one microlight second. But if you calculate how large the observable part of the universe was at that time, it would have been 30 billion kilometers, which is something like 10 times the solar system. So, in a sense, the universe was much, much bigger than it was old. And if you go further and further, closer and closer to where you think the Big Bang happened, this discrepancy, this relative discrepancy, gets bigger and bigger. So in a sense, if you just think about causality, this would mean that if you imagine that the Big Bang happened not at the time where you thought, but this 1 microsecond later, you would need to arrange it such that you would have 10 to the 33 such Big Bangs next to each other, all nicely synchronized. Because the universe afterwards expanded in this very homogeneous and isotropic manner. So they would have had to be extremely well synchronized, all these different Big Bangs. But you cannot do that, right? Because these are not causally connected, these different regions. That's the whole problem, that this would not be, you only had a microsecond, and light could only fly 300 meters, so you could not synchronize anything over regions larger than that. Of course, you can have the expansion of the universe, which changes this a little bit, but not by so much. So if you take the standard Big Bang model, this idea that everything came from a point doesn't seem very tenable. So it's still true that if you look at the equation, you would still have an equation which says something like the size of the universe, A, as a function of time. At early times, if there was radiation, it would be something proportional to the square root of t. So it's still true that when t goes to 0, the size goes to 0, but the way in which it goes to 0 is what's bizarre. Right? It's that you would have to have all this contraction in the very last instant. But we don't really trust physics on arbitrarily small timescales. So, for instance, in particular, if when we get to a Planck time, we would not trust anything on shorter timescales than a Planck time. But if you repeat this argument, you go to the Planck time, you get an even huger number of simultaneous Big Bangs that you would have needed, something like 10 to the 90 or so. So this doesn't seem to be quite right. On the other hand, this was a completely classical picture of the universe. Now we also know that, yes?
Is this related with inflation, like finite space material and what you were expecting, something like that?
Yeah, inflation can help with this, yes. But it does not completely help because, again, inflation does not start at zero size.
That couldn't have started at 0 plus epsilon or...
Yeah, that's in fact, implementing this idea is what I will talk about for a large part of my talk. And yeah, this may work, but you will see. You will be able to judge it by yourself if you think it works or doesn't. Now, inflation would of course change this part. Now, this was the classical point of view, but we know that when we go to very early times to very small scales and very high energies, at some point we also expect quantum theory to become important. And so we would have to incorporate quantum theory. And in this sense, there was an idea which has been around for essentially as long as the idea of the Big Bang. That was that the universe was sort of created as a quantum event. That the Big Bang itself should be thought of as something like space and time tunneling out of nothing. That there would be really nothing, meaning not even space or time, which is, of course, for us impossible to really imagine because we are completely used to just thinking of everything in space and in time. But the idea would be that there was nothing and then that space and time emerged out of this via some quantum tunneling event. So something which classically is impossible, but which quantum theory might allow. And we would then have a kind of a bubble of space and time, which would expand and then which would form the geometry of the universe. But the geometry in a four-dimensional sense. And this would form both the space and the time of the universe. And Lemaitre was maybe the first to really express this idea nicely, or maybe even the first one to express this idea. Certainly there's a paper by him from 1931, which is just 1 page long. This is already a third of the paper, which I have here. But where he says that, in atomic processes, the notions of space and time are no more than statistical notions, that they fade out when applied to individual phenomena involving a small number of quanta. But if you go back, he would say that there were fewer and fewer quanta. So if the world began with a single quantum, notions of space and time would altogether fail to have any meaning at the beginning. That they would only get a meaning later on. That in a sense you start with a quantum, and then as this quantum divides into more and more quanta and the universe grows, only then can you even talk about space and time. Of course, this is a little funny. For instance, he says that if this suggestion is correct, the beginning of the world happened a little before the beginning of space and time. Of course, if you don't have time, you cannot say before, because you don't have any notion of before. But you see, the idea was there. I think the idea, now we would not say it in exactly the same way, because, of course, atomic processes still happen in a space-time. Whereas really one should think of this as the space-time itself being, created in a quantum process. And then, so there are later incarnations of this idea, and maybe the best known and most precise today, even though also not very precise yet, what are known as the no boundary and the tunneling proposals. So the no boundary proposal was proposed by Stephen Hawking and later together with Hawking and Hartle. And the idea of Hawking was that really, let's say we think about the universe, we always describe what happened before. So let's say time goes up in this diagram. We are here, we're describing what happened earlier in the universe, as the universe was smaller. Then we get to a new point here. Okay, so we describe some phase of evolution, but then we have another boundary here. We'd have to say what happened here. Then you say, okay, but I want to go further back in time. You go further back in time, there was maybe another phase of evolution. Say this was the radiation phase here. Let's go back and let's imagine there was an inflationary phase. Again, you say, well, there must have been something that started it. What happened there? And you would have to, you could continue like this forever. But then this is not satisfactory, because you want to have a theory of initial conditions, how the universe began. So Hawking's idea was that if the universe was in some sense rounded off, like a ball, like the surface of a football, then, there is no boundary there anymore. So then you don't have to specify any conditions. If you don't have a boundary, you cannot specify boundary conditions. So you would end this infinite regression by saying that somewhere in the past there was no boundary. That's why it's called the no boundary proposal. But it's important to keep in mind that this means no boundary in space and no boundary in time. And this is what's very weird about it, because normally, we cannot conceive of a geometry which does this. In fact, what it means is that time would have to behave a little bit like space in these early moments, and if that was true, and this is known as imaginary time, if time behaves more like space, then you can round it off, and you can round the universe off. I'll get more into the details of how one could treat this mathematically. But you see, then that's the idea that really, if there was no boundary, then that is the boundary condition, and that this would uniquely specify how the universe came into being. Because then you see there would be no outside. All the space and all the time would be contained in the universe, and there would be, this outside region, which is just in the diagram, would not really exist. There would be no space and no time outside of the universe. And the very similar proposal was put forward by Vilenkin also in the early 80s, which was to say that the creation of the universe should be seen as a regular quantum tunneling event, and the word regular is important. This also again means no singularity, and the only way known to do that is by this kind of geometry, which is rounded off. So in the end, the two proposals are essentially equivalent, even though the way they were formulated initially were different. This would, in some sense, resolve this issue of synchronization that I mentioned earlier. That when you go back to the Big Bang, that you sort of need to synchronize the universe over large regions. Because really, as I just said, this bottom part can only be described mathematically if time starts evolving like space, and in a sense this means that time has to become complex, meaning that the geometry is not a real geometry, but it becomes a complex geometry. I mean, that you need complex numbers to describe it. And this corresponds to a quantum era. Right? In quantum theory, you always have to describe everything using complex numbers. And when you get to the region where the universe behaves classically, it already has a certain size. So this would then resolve this issue of synchronicity, because really then the universe would, as soon as it starts becoming classical, and as soon as you can describe it in classical terms, it's already large compared to the Planck length. And so really, sort of the simplest mathematical model for this kind of universe is the Sitter space-time. The Sitter space-time is a universe which is expanding at a constant rate of expansion, and it actually well describes both the current phase of the universe and a hypothetical phase of inflation in the early universe. And if the Zeta space can be described by this metric, that there is a spatial part which is just this omega-3 here, it's just a three-dimensional sphere. So the spatial part is a three-dimensional closed section. The universe would be a sphere at any given moment of time, but then it expands according to this hyperbolic cosine function. So it expands almost exponentially fast. But if you now take this metric and you make the time t imaginary, so you say my t is now I or minus I times tau, where tau is still again a real number, but I is the imaginary unit. So you make time imaginary, you put this into this thing, this cosh turns into a sine. And in fact, this becomes the metric of a four-dimensional sphere. So what you've done is you've just made this part, you've transformed the Zeta space into something which is only contains space, no time, and the whole thing is a sphere. So it implements exactly this idea that when you make time imaginary, you round off the universe. Okay, so this is the geometry that people had in mind when they were proposing these kinds of this no boundary proposal and the tunneling proposal. The question now is, how do we calculate any amplitude? How do we calculate the probability for having our late universe as we see it with these no boundary conditions imposed? And that's basically what I've been working on for the last couple of years. And I want to explain to you a little bit what kind of calculations these are. Now, a useful way to implement quantum, there's different ways of formulating quantum theory. There's the Schrödinger picture with the Schrödinger equation, there's the Heisenberg picture. But then there is also the sum over histories formulation that Feynman invented, where now if you have a certain, you say you have a particle which goes from position x1 at time t1 to position x2 at time t2. In classical physics, if you know the initial position and the initial velocity of the particle, you can calculate exactly where it's going to go. Or if you fix the initial and final positions and times, you know exactly what the trajectory in between has to be, and there is a unique one. In quantum theory, you would, according to the Feynman prescription, you would sum over all possible trajectories that link these 2 points, and each one would get a number associated to it, which is e to the I s over h bar, where s is the action of the path. So it's the integral over kinetic energy minus potential energy. And different paths contribute different such numbers, and different paths contribute more or less importantly to this total sum. And what you find is that under sort of classical conditions, the path that contributes the most, the dominant path, is in fact just a classical path. But then you can have situations in which something can happen which is classically impossible. Say you have a barrier. You have a particle on one side of a barrier, and the particle does not have enough energy to roll over the barrier. Then, in quantum theory, as you know, there is still the possibility to go over the barrier or to tunnel through the barrier. The likelihood is small, but it's not impossible, it's not zero. Because you sum over all paths that actually connect these 2 points, and there will be a path which connects them. It may not be very likely, but it does exist. And, well, anyway, so this is one of the ways, one of the sort of really nice ways of formulating quantum theory. But now we would like to do this with gravity included. Then, instead of thinking about the trajectory of a particle, we would think about the evolution of the universe. So the trajectory of the particle would be, say, the expansion of space-time. That would be the equivalent. We would say we calculate a transition from a certain for the universe having a certain size, here it's called B1, and matter fields having a certain configuration, chi1, to a later size B2 and matter configuration chi2. And we would then, instead of summing now over all possible trajectories, the equivalent would be to sum over all histories of the universe. So it could just expand, or it could expand a lot and recontract, or it could contract and expand, contract, expand, whatever. Everything would have to be summed over, everything that links these two surfaces. And now the action is given by the Einstein-Hilbert action, so the action for gravity, and in this case we're also adding a cosmological constant, lambda, here. And we're not considering any matter because we want to start with the simplest possible situation first. Now, okay, so then also I should say that, you know, these geometries which are summed over should then not really be thought as the actual physical geometry yet. Right? So in the same way that when you have a particle moving from this one point A to a point B, you sum over all trajectories, but these trajectories are not the actual path of the particle. What you really calculate is just the transition amplitude. And then you can say, you know, the dominant trajectory that contributes is sort of the most likely path that the particle took, but really you can only talk about the measurement being done on both ends. And it's the same here, but now what's in between would be the total space-time. So in a sense, the space and time you cannot really take them as, you know, existing until you've made your measurement on this final hypersurface. Right, and the dominant path would be the dominant expansion history of the universe. You could say this gives you a good idea then of what the most likely evolution of the universe was. But really, strictly speaking, what you would have to do to figure out what the actual space-time is doing is to glue together such a series of transition amplitudes where each amplitude goes to a larger and larger final. So if you're thinking about an expanding universe, each final amplitude would go to a larger and larger region of the universe. And then from this sequence of transition amplitudes, you would be able to infer what the physical space-time was really doing. So conceptually, it's basically like standard quantum theory, but one has to realize that if you apply it to space and time, all the weirdness that you had for particles, you now have it for space and time. So it sort of changes a little bit the way in which you think about space and time. When you get to a region, then the wave function changes just by a phase. And in fact, then if you have something like psi bar psi, which you normally take in quantum theory as a probability, this becomes constant along such a history of the universe. So basically, if you have an entire history of the universe in which now the universe is evolving classically, you can assign it a certain probability. But while you're still in the fully quantum regime, interestingly, you cannot. Because the psi star psi is not constant. You don't have a good, and there's no good substitute. You don't have a good way of assigning probabilities. So in a sense, only when the universe is already behaving classically can you even talk about a concept of probabilities. I just wanted to mention some of these conceptual issues because these are things that I presume you might be interested in, and also that, of course, I would be happy to discuss further later on. But the concrete calculation, concrete question now is, how do you calculate such transition amplitudes? Right? How do you find, for instance, what is the dominant geometry? And this has been something that puzzled people for a long time. And the reason for this is that if you do quantum field theory, there is a standard trick that people do to calculate these path integrals. And this also has to do with time being treated as an imaginary parameter. And this is what is called a Wick rotation. So you have the integral that you're trying to calculate. The integral that you're trying to calculate is over e to the I s. But now take the example of just e to the I x squared. See, if you take the real part of this integral and you plot it, this will oscillate faster and faster. It's a highly oscillating integral. With the Wick rotation is to treat your time as an imaginary component, and this changes this oscillating integral with the I into something which is just suppressed, something which is like a Gaussian integral, and which is much easier to handle mathematically. But when you include gravity, this trick doesn't work. There is a term in the action which corresponds just to the expansion of the universe. So the kinetic term for the size of the universe has the opposite sign than the kinetic terms of all other fields, of all the matter, for instance. But gravity is different. This has to do with the fact, in fact, one can show that this has to do with the fact that gravity is purely attractive. There are no, in electromagnetism you have positive charges and negative charges, but in gravity there's just one type of charge, just mass. There's no negative mass or anti-mass or whatever. There is just mass. And gravity is always attractive. Now, the fact that you have this different sign here means that when you try and do the trick of transforming your integral from oscillating to convergent, you make it divergent. And so it just doesn't work. Yes?
Is this related with gravity not being renormalized?
No, this is a different problem already. This is simply, this is a separate problem.
I just was curious that you brought in the mass as the sort of the charge that's always attractive in gravity, but you said we were working in matter-free universes, just geometry so far.
Well, still, it's built into the structure of gravity. So I still have general relativity built in. And so you can even think of the fact that, gravitational waves, so waves in space and time themselves are attractive. They also have so mass in the sense of energy and mass. Any energy will always contribute in the same way to the Einstein equations.
Because the cosmological constant could go either way. In a sense, it's repulsive if you take the right sign.
That's right, yes. But this is not... So this depends on your point of view, whether you treat this as an exotic type of matter or as part of the definition of gravity. So let's see, what's the best way to think about this? I mean, it's true that a positive cosmological constant is repulsive, but it doesn't change the fact that it doesn't change the structure of gravity itself. If you put in this universe, you put two stars, they will still attract each other. And anything in this universe still attracts each other. It sort of gives an overall energy to the vacuum, but not. It doesn't change the way in which gravitational interactions themselves occur. I meant more sort of the gravitational interactions directly. They are always of the same sign. Now, so the way in which we could make progress with these calculations is to use a part of mathematics called Picard-Lefschetz theory, which is a more formal mathematical way of dealing with such oscillating integrals. So, if you have Feynman's path integral approach, you always have, if you stick to real time, you always have the problem that you have these oscillating integrals, where you don't know if they will converge or not. And Picard-Lefschetz theory is a way of defining these and of calculating their value. And the idea is that you actually view these integrals now as where in an extended field space, where each field that you're looking at, you consider it now as a complex variable. So, and then you know from complex analysis that if you have an integral over a complex variable, you can change the contour of integration. This is what Cauchy's theorem tells you. You can change the contour of integration without changing the value of the integral, as long as there are no singularities present. And of course, as long as you keep the endpoints fixed. And in a sense, Picard-Lefschetz theory is a way of finding out how you should change the contour of integration in the most beneficial way. So if the idea is that you have an integral which is highly oscillating, say the integral is along this orange contour C, and it's highly oscillating, the idea would be that you keep the endpoints fixed, but you deform your path over which you integrate. Now in this extended field space, you deform your path, and maybe along this path here, the integral is nicely convergent. These paths over which the integral is nicely convergent are called Lefschetz thimbles. A thimble is this thing that you use to protect your finger when using a needle. And I'm guessing that maybe because of this shape, this is why it's called a thimble. So the idea would be that now you try and replace these integrals, right, which you do not know how to calculate, with integrals which are nicely convergent. And you see also, if they are of this shape, then the value of the integral itself can be approximated by the value here at the maximum. And in fact, in this complex space, this maximum is really a saddle point. So there will be other directions in which the value of the integral is growing. But along this thimble, there will be a maximum, and this will help you to approximate the integral. Just to have a rough idea, how much time should I use up?
You have under 10 minutes.
Okay, good. Just to know into how many details I should go or not go. So maybe I can. So the Airy function provides an example of this, but I think in view of the time, I will just skip it. Really, the conceptual issue is simply what I just said, that you find a path in the complex field space along which the integral is nicely convergent. And the nice thing about Picard-Lefschetz theory is it gives you a systematic way of doing this. It tells you exactly how to find such a path. So let me just go back to this diagram. The way to do it is you look for all of the saddle points, so for all of such potential saddle points, such as this one here, and you see the original integral had lots of cancellations. So that means that now we replace it with something which has no cancellations. That means that the value of this integrand must be smaller than the typical value here, because we won't get these cancellations. And so that tells us in which direction we have to deform the path. It means we have to find the directions of steepest descent, so where the value becomes smaller and smaller, and we just follow that direction. And then we will automatically find the appropriate such contours which we should use to define the integrals. Okay? So we just have to follow this procedure, that we follow the direction of descent, and then we will find the correct integral. These saddle points, they can have various values. So if at the saddle point all the fields have real values, this is what corresponds to just standard classical physics. Because this saddle point, in a sense, is the dominant geometry that contributes. It's the most likely space-time. And if it's real, then we just get back a classical solution of the equations. But if it's a complex saddle point, this we can interpret as being in a situation where quantum effects are important. So the fact alone of whether a saddle point is real or complex already tells us whether we have a situation that's essentially classical or quantum. And there can even be situations where you have more than one saddle point, and then you have something which is like a quantum interference effect, where different possible histories interfere with each other. So now we want to calculate this for gravity with a cosmological constant. I don't think there is much. I should go over the details here. The idea is to find good variables. So if you take the standard metric, which is just to have a function n which determines how much time elapses, and a function little a which just tells you the size of the universe, the scale factor of the universe, then the action is still very complicated. But there's a system of, there's a field redefinition that you can do, in which you now call the size of the universe squared q, that's your variable, and you change the way that you measure time. You just define this function in front of the time part to be n squared over q. So this just means that the time that you're using is not the physical time in the space-time, but it just happens to be a convenient time variable. If you do that, the action becomes very simple. You get a canonical kinetic term and a simple linear potential for q, and where q is the scale factor squared of the universe. So the advantage of this is that you can now do almost all of the integrals exactly, except for the integral over the time n. So you end up with an integral that your transition amplitude is given by an integral only over this n, where n is the lapse, what's called the lapse function, only which gives you how much time evolves between two configurations. And so now we want to, this integral is however very complicated still, so we want to apply this Picard-Lefschetz theory to it. This means we should find all of the saddle points and then figure out which ones are the relevant ones. Now, this is something that one can just do numerically, for instance, and then plot the saddle points and then these lines of steepest descent. Just showing you a numerical example because it looks nice, but this is of course not informative. Here would be a more informative diagram, but not, less nice. This would be now the complex plane of this lapse function, meaning that if I'm here at 0 in the center, no time elapses at all between two events. Here would be a positive real time between two events. Here would be a negative real time, which would basically mean I'm going backwards in time. But really, we will look at the integral in the complexified region. So in the orthogonal direction, we have just this would be the imaginary time direction. Okay. The idea of doing these integrals is to deform the contour. So really, what we want to do is we want to sum over all positive real times, this orange line. As we want to take this as our definition of the integral, but now we will deform it as which is a mathematical trick, which is not, we're not really saying these are complex times, we're just saying this is a mathematical way of doing this integral. Then when we follow the direction of steepest descent, we find that only one of these four saddle points, there's just one of them which contributes. So we find one dominant geometry, and it is complex. And this is, of course, what's expected, because having a universe that has this no boundary condition, this cannot happen classically. So it is, of course, completely normal that we will find such a complex quantum saddle point. So this will be the path, the preferred path. It's a technical point. And then you can just calculate what the transition amplitude is. The precise form is unimportant. It would just mean that, but the probability depends on the cosmological constant, on the vacuum energy lambda. And the probability turns out to be not the one that Hartle and Hawking had conjectured that you would get, but it's the inverse of that. And this has important implications. The most important implication is the fact that we're not just interested in making a universe which is just large and completely smooth, but we know that we have all sorts of stuff in the universe, so we have to check what is the probability for making a universe that's more curved at later times, where there are, changes, local changes in the curvature or anisotropic deformations in the curvature. So you can add perturbations and then do the calculation again. What you find is that these curved geometries are more likely. They have a higher probability. So you start out smooth, but then the universe evolves into something very curved. And this has a higher probability than if it was very smooth. And the more curved and the more anisotropic it is, the more probable it is. This makes no sense. Because it would mean that the highest probability would be for the most curved universe. But if you have a universe that's extremely curved, it will immediately recollapse. It will not expand into a large universe such as the one that we know, but it will immediately recollapse. So from this we concluded that actually this way of calculating that the universe starts from nothing, from zero size, going to a finite size, this does not work. Okay, this was the situation a few months ago, that we had just found that this calculation does not work. So in the last couple of minutes, let me just tell you about a recent calculation that my student Alice Ditucci and that we performed. And this is, I have too many equations here. I will just explain the concept. Now, the idea that the way that we implemented the calculation was to say we start from a universe with zero size, we go to a universe with a finite size. But in quantum theory, say you measure a particle's position and velocity. You know from the Heisenberg uncertainty principle that you cannot measure both arbitrarily accurately. So if you measure the position of a particle with more precision, you know its velocity with less precision. You have more uncertainty in its velocity, and vice versa. So what we did in the calculation that I just presented was to say the universe started with zero size. This was precisely imposing zero size, exactly zero size. This means that, in a sense, the equivalent of the velocity of the particle for the universe is the expansion rate. This means that we had an infinitely uncertain expansion rate, because since we said we start with zero size. And so the one thing which we tried recently was to say, well, what if we spread the uncertainty? What if we say we started with approximately zero size and approximately such and such an expansion rate, instead of saying we started with precisely zero size? And if we can specify the expansion rate, this is in a sense allows us also to specify this rounding off, because this rounding off is like having an expansion rate that goes into the imaginary time direction. And so if we say, imposing not this initial state where the universe is of zero size, but only of approximately zero size, allows us to also specify more precisely that we want this rounding off to occur. And so when we did this calculation, we found that actually this does work. Okay? So this actually works. This gives us the stable situation where when you add perturbations, when you add curved universes, they become less likely than the smooth universe. Now, what does this mean? In a sense, what this means is that, we don't really have no boundary. I would say rather that we have a kind of a fuzzy boundary now. Because when we say we start at zero size, then really we have nothing. But if we say we have sort of approximately zero size and approximately a certain expansion rate, then the universe there is already something there, in a sense. There are already fluctuations of space and time. So we start from a certain quantum state which already contains fluctuations of space-time. And so I think that in the sense of implementing the idea of quantum tunneling out of nothing, it fails. I don't think one can say that you tunnel out of strictly nothing. However, it does give you, as the most likely geometry of the universe, precisely this kind of geometry where you don't have a boundary in the past. So in this way, we can implement this idea, but I think at the expense of not really realizing the original idea of coming out of completely nothing. So this is, I don't really know what to make of that. I'm just telling you that this is the current situation of how I interpret the calculation. Then, of course, we have, because it's a quantum transition, there is sort of a most likely evolution history of the universe, but then there are probabilities for completely different ones. So there would even be, in principle, a probability which is non-zero, though ridiculously tiny, that the universe would just have come into existence right now. This is, of course, then implied, because you have this initial state with fluctuations, you could just immediately fluctuate into the current state. But of course, this is consistent with quantum theory, and the probability for something like this is extremely, extremely small. But really, I think that the most important implication of this is that you sort of already have fluctuations of space and time before you make a large universe containing space and time. And whether you can sort of truly start from the absence of space and time remains an open question. And in the current framework, I do not currently see how this is feasible. And also, I don't know of any other quantum gravity model that can currently implement such an idea. Because typically these ideas are not formulated with very, very precisely. We tried here to formulate the idea as precisely as we could, and this is where we end up. So that would be the current situation. Thank you.